We're trying to catch up. We're going to talk about Cubesat design and launch. It's the very technical session. We're going to have Dr. William Edmondson, who is CEO of Max IQ Space. He and Judy Sandrock have been really leading in terms of getting us ready, getting everybody prepared. I was very impressed by the roadmap that she shared earlier, and we want to hear more about the actual CubeSat process. I know that ATI has a project that is going to be on. They have the high altitude balloon project. I tried desperate to get Jamaica on the board on stream. It didn't happen. I'm not sure if Guyana was able to get in as one of the 5 countries, because we have a mini project with them, with Jamaica, Guyana, and Trinidad and Tobago, but everybody's at different level of an accomplishment. So I don't think the Caribbean is in it this year. Hopefully next year they'll make it. So Dr. Srimathi Kisan is here. We have Dr. William Edmondson and Dr. Omar Imam. So let me just introduce them again. Dr. Srimathi Kisanan is with Space Kids India. They already do a lot of training and design and building and launching of CubeSats with young people K through 12 India. Dr. Edmondson is with Max IQ Space. He's already been introduced to the organization. Prior to that, he was a professor of electrical engineering. And you already have met Dr. Omar Iman this morning, Interspace Association. So where is my moderator, Joseph Quanto? He's part of the All Nation Space Lab, and he'll be moderating this session. Thank you.
Thank you. Good afternoon to you all. Thank you once again, Madam Chair. Good afternoon once again. I believe you are all enjoying the session so far, those here and also those online, even though it's been a long day. I'm moderating on the CubeSat design, development. Please, are they? All right, so sorry for the interruption. I tried to sort one or few things here. Yeah, so as I already said, I'm moderating today's session. This session on CubeSat design, development, launch, and operation. As we all know, CubeSat is a standardized satellite development platform that over the years was proposed by Prof. Twig and Jody to provide easy access to space. And this was somewhere 1998. And over the years, we've had a lot of satellites launched to orbit, I think about 4,000 CubeSats. And this has been adopted by institutions such as those in academia, space startups, and developing countries like Ghana and so on and so forth. This is because of its simplicity in terms of development and launch. And this standardization, as most of us know, comes with standardized size, structure, launch and deployable mechanism, as well as frequency for publication and operation. Okay, so with this simplicity in the development, the design, development, and launch makes it easy for everybody or a lot of people to come on board to also explore space, science, and satellite technology, and also see its utilization for humanity and also addressing the SDGs, as we all know. So in this session, I have speakers with expertise who are doing remarkably well in this area, as Madam Chair had already mentioned their name and their institutions. So, and you know that Cubesat being easy to develop is more preferred compared to the traditional method of satellite development. And we know that when it comes to traditional satellite development, it comes with spend a lot of time, a lot of funds, and you need a lot of expertise, okay, in developing satellites. So you realize that it will take a long time before one satellite can be launched to perform a particular mission. But with the platform of Cubesat, it gives easy access for people to come up with missions and do experimentations and so on and so forth. So I'll be glad for our speakers with expertise to also share what they have and what they have been doing for us here and those online to also learn. And I want to say hi to Dr. William Edmondson. This is Joseph from Ghana. If you remember, he has been here before. All right, so I'll allow Dr. Kizan to be our first speaker for this session. So please, if you are ready, can you give us a confirmation and you can please take over from here. Thank you.
Good evening, everybody. So it's been an interesting 2 days, I should say. This is Dr. Srimati Kesin, founder CEO Space Kids India, and you have the kids in between space and India, so you know what it means. We're working with children. We want to make space as accessible as possible, saying that we are the only organization in India who've built about 26 space missions, of which we have about 4 orbital satellites, 3 suborbital, and 19 of which are balloons. If the chair permits and if the panelists permit, I wish to share a brief video which summarizes the entire journey of Space Kids India. May I?
Yes, please, you can do so.
Thank you so much.
Cubesat launch किया.
Cubesat, and they are the first customers. Let me compliment and congratulate the team.
Thank you for this wonderful video shown to us covering everything you've been doing in India. Thank you very much. So you can continue with your presentation, please.
So thank you so much for patiently watching that video. Well, these are the 26 missions that we have embarked on, and it's all with us, done by students, designed, built, and launched between the ages of 14 until 21 years. And now moving on, I can show you the real engineering model of a microsatellite that we had built year last. So we've been building femto, Cubesat, and the latest one is the microsatellite, which was built by 750 rural girl children of India. So so we started off with the femto category, which was 64 grams that we had launched from Wallops, Virginia, NASA, and then moved on to launch a 1U CubeSat, which is 10 into 10 into 10 centimeters, with wanting to know about the temperature and the radiation in space. So we built a 1U CubeSat that was launched in 2019 by ISRO. And then subsequently, we wanted to build a bigger satellite, a microsatellite. This is a 12-kilogram satellite that we had built. And this had involved a new technology where on the ground, it was 8U satellite. And when it went into space, it expanded into 64U. This is predominantly for the power consumption, because power is the most critical and challenging segment in the entire, be it CubeSat, microsat, or any satellite. That is the most challenging segment, and the communication. So that is the reason what we did was we worked on this expansion model. Of course, it worked for a while, but then I think it requires some more R&D to it. So this is the journey, and Cube satellites, yes, of course, is picking up, and now we are coming up. Azadi-Sat being a prelude for Shakti-Sat, Mission Shakti-Sat. We want to bring in 108 countries together to build in a spacecraft to be launched into the lunar orbit. I understand it's an absolutely adventurous and challenging mission, but there are hardly about 60 nations in the world. Of course, the table shows 80, but 60 nations, and more so, predominantly only 5 countries who are working in the space domain and who have an industry per se. So space being the future, we want to bring in everybody together. So that is the reason, and all the more girls into this industry, and build this spacecraft, which is going to be unique. So I would really wish and request all your support for the same. And thank you, Dr. Claire, for giving us this opportunity. Thank you.
Thank you very much, Dr. Kizem, once again for this insightful presentation and what you and your team are doing over there. We are so much impressed with it. And
thank you so much.
I have one question, then maybe we'll move on to the participants here.
Yes, please, go ahead.
Okay, so before we move on to the next speaker. Okay, all right, so before we move on to the questions and answers, the other speakers will do their presentation, then we can come back to that. So sorry for that. So I will have Dr. William Edmondson also present to us what they are doing.
Okay, can everyone hear me? Good. So if you don't mind, I'd like to share my screen. I just have a small presentation.
All right, sure, you can please do so. I believe you have access to share the screen. If you don't have, then you...
I do.
You do.
Thank
All right,
you.
great. Okay, thank you.
So again, I'd like to thank the committee for inviting me. And yes, I've been to all nations and would love to get back, see what you guys are doing and how you've grown. But what I want to talk about today is more on how we educate students, particularly at the graduate level, with a focus around satellite design and development. As I've been part of the Cubesat movement for quite some time, and one of the big issues was the design and build, but not a lot were successful. And so how do you make sure that your design and build is at the end actually works? And so part of this is what type of education that needs to be put in place, particularly at the undergrad and graduate level, to ensure success. And so my talk is, Space workforce education, particularly around a model for Africa. Just to give you a little bit of background, because I think this is important. Yes, I am a member of MaxIQ. I've been introduced as the COO, but one of the things that we've done at MaxIQ is we've not given each of the founders a title. So we're all called founders, and we just do the work that needs to be worked. So, so Judy has already laid the foundation for what we do. And since retiring, I'm actually an affiliate faculty with the University of Hawaii in Manoa as part of the Hawaii Institute of Geophysics and Planetology. And so a lot of my talk is based around the work that, in terms of curriculum development, that we've done there that I think can and should be ported in specific ways to various institutions on the continent and actually throughout the world, particularly with a focus on Southern Hemisphere. I also have my consulting company, Sedana. I am the founder of that. And it's really just consulting around communication, systems engineering, and education. So the program at Hawaii is defined to be Earth and Planetary Exploration Technology Program. It is interesting, not in the School of Engineering, but in the School of Sciences. And we've sort of generalized the term or defined it as space systems science and engineering because it is a collaborative effort. It is an interdisciplinary effort that brings together both the science side, the engineering side, working together to solve a problem. And so this program was motivated because we felt that there was a significant increase that needs to occur in the industry, particularly for women, people of color. And so that's sort of been our focus, particularly since we're in Hawaii. We wanted to provide an innovative approach for increasing and educating the space workforce, but we also wanted to have ability to port to other institutions, or at least with companies for new employee onboarding. And we'll get into some of the details. But the other perspective, and this is something that's been going on within the Hawaiian and the Pacific Island nations, is how do we decolonize those efforts? And that means how do we bring into more of an indigenous way of thinking and its view of the universe as we become, as these communities become space explorers. And I really shouldn't say become, because if you look at their beginnings, their origin stories, they were always, space was a big proponent in that. And in fact, how they got from island to island was based upon the stars. And so you'll see this, but presently we're actually writing proposals on how to integrate this decolonizing perspective amongst the Hawaiian, the Maori, and Aotearoa, that's actually New Zealand, and the Pacific Northwest, the Coast Salish in North America. And so to give a description of the course or the program, we can think of this as a 4-semester course. The first part is Introduction to Space Systems Science and Engineering, where the first course is Space Systems Science / Engineering, so it gives you that general overview. The second course, I go into more detail on the science side of things, but also how do you create a science payload? So we actually, the students in the first year, actually determine what science they want to do, how to go in terms of payload development. And again, this is all around Cubesats. And then in the second part of the course, that's where you actually go ahead and design, build, and launch. And so they go into mission design and then finish things up with their capstone project. And at that point, it is the hope that the students have designed, built, ready to launch, and just waiting on a ride. So the goal and structure is to provide students with a complete experience of design, build, and launch of a CubeSat based upon a science payload. And the students determine what payload, and they actually go and write proposals to NASA to get the payload funded. So they also understand or have experience in writing proposals, semi-business plans. In terms of delivery, we put it in block mode options. And so we have a 2-year cadence, and this is for 1U mission types. So these are the smaller. But if the missions are science payloads are more complex and require something larger than a 1U, then we have a cadence where we can spread that over multiple years before launch. And there's actually a handoff between the different cohorts, such that the hope is there's a smooth transition. We also created or designed a summer school such that we can do all this over the summer, but also we can segue this into a graduate program. And so what is the program innovation that I talked about before? And so really it's about having a design philosophy based around systems thinking. How does one develop technology, not only with an understanding of its behavior within its environment, but also the community? So I think in the previous talk, in the last session, someone talked about having the community get access to this data. How should that be done? What data is needed? So there actually needs to be communication with the community to help determine what actually needs to be measured, solved. But also from a second point is how we think actually and see informs this design. And this gets into, from a cultural perspective, how do we solve problems? And so community worldview represents a key input. And this even includes the language. So we think differently depending on what language we speak. Um, and that's a proven fact. And so those are some of the key components of developing a decolonizing curriculum. Now, sort of just put this in a simplified block diagram, particularly those of the Southern Hemisphere take on a relationality type view of the world versus more of a European American centric, which is more rational. And so some of the key components of relationality is I am human because I belong to the community. Collective ownership, but that community means all things living from Earth to space. So there is no delineation between the ocean, the earth, air, and space. But there's also a generational connection, the past, the present, and future. And in fact, this actually, in terms of relationality definition, this defines the spirit or the consciousness of the people. And this is is different from a Eurocentric view, which is, I think, therefore I am, self-realization through mastery of nature and very individualistic. Furthermore, in terms of program innovation, we definitely bring in that relational design strategy, where here the universe is a complete system. So what happens on Earth informs what happens in space. And so we need to consider the interconnectedness of place, people, and things in how we move forward with our design. The other key important point or innovation is that the program is transdisciplinary. So this is more than multidisciplinary. And so seeing the world more systematically and holistically and designing a CubeSat is not just the MEs or the aerospace engineers, it's the EEs, it's the business people, it's the community, and bringing everyone together to help solve this problem. But another key point, particularly with CubeSats or any satellite system, in a way, these are complex systems, and they're made up of a combination of not only the physical system, but also networking, tying all the subsystems together, but it's also being controlled by embedded computing. And what we found, and not just in the space industry, this is also true in the automotive industry, is that a lot of times you leave software development within your design as last, because, you know, people think it's easy, it's the last thing. But it is, and that is how and the reason why most missions fail, or you have this long redesign that needs to occur. And so one of the things we're pushing is develop the software, understand the software architecture as we develop the satellite system itself. So I think that's an important concept. But we're also implementing modern space systems engineering methodologies and processes. This is to ensure not only that we design it right, but that we come up with the right design. And so I'm going to leave it there and wait for questions and answers during the Q&A period. So again, thank you, and thank you for the team.
All right, thank you, Dr. Edmondson, for giving us an overview about your education system for space engineering at your graduate school. Our next speaker will be Mr. Solomon Akpe from Xavier Space Solutions. Please, if you are online, Can you confirm for us, please?
Yeah, hi everybody. I hope you can hear me.
Yes, please, we can hear you. So you can please go ahead with your presentation.
Brilliant. Thank you so much. I'm sorry I'm not able to turn on my video as I have network issues. All right, so just a minute. Okay, please let me know if you can all see my screen now.
Yes, yes, please, we can see.
Okay, great. Okay, so whilst I try to get my slide into the okay, there we go. So I'm a picker, a young space scientist solutions, which is a space startup in Ghana. I'm also a young researcher at the University of Leeds, where I study young massive stars. So in this presentation, I'll tell you a little bit about what Xavier Space Solutions we do, slightly related to what Cubesat in general is, and also moving on to what we are currently working on, which is more on miniature satellite, which is pocket cubes. So just next. Yeah, so like I've said, I do most of the time, I do space stuff in the sense of satellite development, R&D, and I like also getting my hands dirty in actually designing some of these things. And also at sometimes I'm also involved in doing astronomy research, and the image on your left there shows my office in at the University of Leeds. So to cover what I want to talk about in today's presentation, I'd like to talk about how our startup started from just doing space outreach to actually developing what we call experimental satellite or CubeSat to what we are currently working on, which is on CubeSat and also on Pocket Cubes. So as you can see in this diagram, we did started off with just going to schools, talking to kids about the need for the study of astronomy and space. And as most people would know, in Ghana, we do not have a formal education in astronomy or space science. And to be maybe a bit more update, I should say that I think we have a lot of development. For example, the work that All Nations University I've been able to do in the past, and some of the other work that I know some of my colleagues in Ghana are working on. I think we are closely getting to the point where we would have formal education in typically astronomy and also space science, where you can actually have students involved in either building some of these systems from the basic level onto those other levels. So that's how we started off, and I'm going to show some of the experimental satellite or CubeSat models that we have been able to build. And the reason why I feel this is important for us to share or for people to know is because I'm pretty sure most of the other speakers in this section or in the entire conference would agree with me that most either startups or most countries, especially for the African continent, it's usually difficult to start off by say, oh, I want to build a 1U CubeSat or 2U CubeSat without the development or the prior development of the field in the country itself. And that's one of the things we realized quickly, which is why we started off the way we started off. So we have, over the past, I should say 3 years, we have been able to engage about 600 plus students. And these are students from the ages of 11 years or 12 years to 18 years plus. So that's covering the elementary schools, which is in Ghana, and also the secondary and also the universities. And what we found out was that it's very interesting that you have a lot of students who actually have interest in directly either building space systems or at least being involved in either programming some of the microcontrollers, for example, of these systems in order to be able to not just solve problems in the environment, but also sort of build a career out of it. So these days, so the last campaign we had was last year, and it was funded by the IAU's Office for Astronomy Development. And these days, what we do, like I've said earlier on, would be to move on to developing things that can actually go to space. In that sense, we do have our prototype CubeSats and also the pocket cubes that I talked about. I think I do have a few images of these things, which I'm going to share as we move on. And I think before I go to the next slide, I should say that there are several examples of either countries or space startups who have gone through this process. And we at Xavier Space Solutions believe this is a model that for African countries, to be specific, or developing countries, I should say, it's a much easier path to go to be able to develop this satellite, rather than just starting a very complex, as we all know, mission to say, oh, I want to build a 1U CubeSat, where people don't actually even understand the basics of these various systems. And maybe finally, or to also say that this has been shown to be a sustainable approach to actually being able to develop, whether a CubeSat you want to develop, a pocket cube, or maybe a much, much bigger satellite for different processes. This is a sustainable path. And one thing that I think is also important to highlight is that at the end of following something like what we followed, you realize that any country, or let's say any institution that would be involved in this, actually ends up developing their own maybe subsystems or things related to these things, which I believe is very, very important, because I think one way that say we may fail in let's say a space program is you could begin easily by developing or maybe collaborating. I'm not saying collaborating is not a good thing, but what I'm trying to say there is maybe getting components to do stuff, not really going through the various basics, hinders the growth or how sustainable these various projects would be in the end. So I've put a few benefits of why such an approach is important. Like I was just saying, it's a way to actually develop space-ready hardware and software, which Xavier Space Solution is an example of. It's a cost-effective because you can start with a very small budget and move on as you go on. And also very, very important, at the end, you actually have students or young people being involved in these things, which actually builds them towards the career that they want to get to. So these are a few images of some of the modules that we follow through some of our concept or experimental satellites training. And these are images of our modules. So these are modules that I should say that we have tested at altitude between, say, I think 100 to about 100 meters, where you can see that we have different parts of this experimental satellite module, where we have, we do use the ESP32 micro controller and use this in different ways. I'm sure the data sheet and those things are stuff we can share. You can customize this to different purposes. You can even use this for as, let's say, a weather station, or maybe if you're interested in IoT, you can connect several of the communication modules that we have built here to be able to do some of those fun stuff. So these are just more images. And so, yeah, I did also say that at the end, we develop a software, which, as you can see, this is the view. And it's important to say that this does not just develop the space hardware part, but you also get students who are interested in either programming or coding. And this is very, very important, as you are able to sort of cover different interests of students. Again, these are some of the specifications which I'm sure we don't need now. And I've pretty much talked about the education aspect of it, or how this is important. And we have several collaborations, and I think what we want to see in the future is see either secondary schools or universities put some of these say trainings into their modules so that students can get access to that. So I think in the final slide, I'm just showing some of the images of the pocket cubes. So we are still in the design phase, and once we get to the end where we test everything, we can actually do have a press release and talk about all these things. I should say that thank you so much to the organizers for giving us the opportunity to talk about some of the things we are doing. Perhaps it doesn't directly go on to the theme, but I think we have gone through the process of actually developing prototype Cubesats, which I'm sure is just one small part of being able to develop a sustainable space program in the, say, big scheme of stuff, or also be able to get countries started in building systems like this. So once again, thank you so much to all the speakers. I think I have enjoyed the various talks so far, and yeah, thank you.
Thank you very much, Mr. Solomon, for coming up with this concept model to train the younger ones. I believe it's well affordable for our people in Africa to be able to also patronize.
Indeed, indeed.
Yeah, we'll come back to questions and answers. But now we will move on to our next speaker, in the person of Dr. Omar from Intospas Association. Dr. Omar, please, are you online?
Yes, I'm here, so I'll share my presentation. So thank you very much once again for the opportunity to present here. And I know I presented earlier this morning, but I'm not sure how many are here. So I'll go very briefly with these slides and then maybe highlight the points which I think I would like to talk about. And maybe a lot of the earlier speakers covered a lot of the things I was going to cover, so I'll be brief with that. So, I mean, I've been working in the space industry for 40 years now, from the 80s, working on the Mir space station, on the space shuttle, working with the institutional organizations at academia, and then moved to industry, worked at what was then Astrum, then Airbus, developing things like the Mars ExoMars rover, as well as commercial communication satellites. And I was lucky to develop the payload work for Gaia, the Gaia telescope, as well as the payload for Inmarsat 4, among others. Then I was very fortunate to be invited to participate in supporting the setup of the UAE Space Agency and the National Space Science Technology Center there. And this is where a lot of the Cubesat activities that I will cover were developed there as part of the educational program that we set up, that was both undergraduate and master degree space systems program, through which we were able to get the students to develop and launch CubeSats at various sizes and various sort of applications related to remote sensing, as well as navigation and so on. So that's really a very quick overview of what I've done. I hope you can see the presentation. Yeah, okay. So basically, yeah, I can't seem to be able to make it. Okay, yeah. So I've set up, since I've returned from the UAE, I've set up this association, Interspace International Outer Space Association, that is intended to promote collaboration at the international level to work on projects that support Earth sustainability using space assets. That's really the main aim of that. So I'm going to go very quickly through this because I showed this earlier this morning. So our main objective is to have these. Are you able to see my slides correctly? Because on my side, they're not showing very well. Can somebody just tell me?
We can see the slide from our end.
Okay, that's great. So we are doing so 3 really core initiatives. And this is the space program activity, which is basically satellite space missions and research development, and then the peripheral activities, which are to do with the data centers, ground support, and also the institute instrumentation for data validation and improving data quality, and then of course the education and outreach. We have at the moment 23 active expert members who support the various activities. Our aim is not to do everything ourselves, but to collaborate with entities across the world to support various things such as outreach and education, but also the development of technologies and research. The main activity that we're focusing on at the moment is identified a gap in coverage over Africa and the Middle East in terms of air quality that allow us to get data at a very high rate. So currently, we might be able to get data every 24 hours or even less, depending on the sort of type of data we want to get, if it's high resolution, hyperspectral, for example. So for that reason, we picked up on this topic that is really important to the health and the quality of life for people living in the region. As you can see from the statistics, the mortality rate due to air pollution, it comes only sort of third after high blood pressure and smoking. So being able to monitor that and manage it, monitoring that from space, and that will allow us to help us manage this on the ground. So the aim is really to set up a global air quality network that includes data from a lot of the satellites that already exist, but also the satellites we are proposing as part of this initiative to be able to develop and launch in space. So this activity is called the MEASMA program, and that constitute 2 elements. There's a geo satellite, which is based on we're taking the tempo and NASA tempo as a template, and then we will discuss within the regional experts and scientists to see what the real requirements are for monitoring air quality in the region, so that we can then define the requirements for the payload for this mission. And this will be a geostationary satellite system. The other one is a LEO satellite constellation based on Cubesats, and I was fortunate to be the electronic lead for the development of the payload for this, using quite innovative technology, which is referred to as a solar occultation using laser heterodyne spectroscopy. And that will allow us to measure through slices of the atmosphere with a precision of 3 kilometers to understand exactly what the constituents are from 6 kilometers up to 80 kilometers in altitude. So all these will cover things like greenhouse gases, dust storm in terms of aerosols, as well as pollutants like nitrate compounds. As you can see from this slide, this was generated by CEOS, and you can see there is a whole gap over Africa and the Middle East, which we hope to cover by the MEASMA Geo North and MEASMA Geo South, but also other areas are also lacking, which is South America and Australia, which maybe in the future we can then support. The reason I'm also showing these sort of 2 projects, because they're really extremes, 2 extremes of space systems. So the MEASMA Geo is really a very sort of traditional sort of type space instrumentation. The instrument itself is like 1 cubic meter, and I hope you can hear me with the noise. There's workers outside. 1 cubic meter, 150 kg. This is just the instrument itself, and that actually sits on a telecommunication satellite, which is like a double-decker bus, basically. In this case, is the big communication satellite shown in the picture down the bottom. And this satellite works in the UV band that allows us to monitor a lot of the various gases, some of which are good, but some of them are not, such as low-level ozone, and also some of the nitrate gases, as I said, but most importantly, dust and sunstorms. So in this image, you will see on the left, this is a simulation done by the World Meteorological Office in Barcelona, where they done simulations of the dust based on in situ ground-based instrumentation and predictions, as well as some data from Sentinel and so on, to show how the dust is moving around the Sahara Desert and also the Middle East. While on the right, this is actually real data from an instrument called GEMS, which is very similar to TEMPO, that was launched by the South Korean Space Agency, again built by BAE Systems with support also from NASA. And you can see this is actually real data updated every hour across the whole region. So our hope is that with this instrument Miasma Geo, we'll be able to cover the whole Africa and the Middle East with data every hour, almost real time. So therefore, what you see on the left, instead of being simulation, will be real-time data that we can then gather. And that's really important to be able to understand how, in this case, dust, but also other gases transport across the region. And in fact, some of these dust pollutants actually transfer all the way to Europe, but even to the east coast of America. So it's not just a regional issue, but it's a global issue, and that's why it's important to be able to develop such instruments. On the other extreme, of course, is the Cubesat, which also supplement this whole program. And as I said, a Cubesat here on the right is a demonstrator Cubesat, which is a 6U that includes this highly miniaturized instruments. These instruments currently do fly on NASA and ESA projects, but they are very large. You know, as I said, they're of the order of 100 kg or so, but we managed to miniaturize it at Red at Appleton Labs in the UK with support from ESA and the UK Space Agency into a size that can actually fit in a CubeSat. And the idea is then to have a constellation of these satellites that will then allow us to get the high revisit and high sort of spatial coverage of the gases, not as across just the horizontal, but also across the vertical. So this allow us to get very good data, again, low altitude ozone, but also greenhouse gases and so on. To be able to get precise data and good quality of this data, as I mentioned this morning, we really need a lot of in situ ground-based equipment to monitor air quality and also pollutants and of different types on the ground that will allow us to validate the data coming from space and generate the high quality that is needed. And it's really important that these equipment are localized, because different geographic locations will actually have different characteristics in terms of albedo, in terms of the constituents of the ground reflection, in terms of the nature of the atmosphere, that need to be calibrated depending on the local data generation. And this is really the first stage of this program, where we try to then educate at the university level, but also the research establishments and Met Office people work in Met Offices, to be able to understand how this data is processed and how it could be used to then do prediction, but also to validate the data from space. I'm not going to go through this very much, because I think everybody now knows what CubeSat is and why it's really cost effective to do that. Also, colleagues touched on the different sizes of CubeSats. So CubeSats fall down in the range of sort of the small size of range of CubeSats, starting from 10 centimeters cube, but gradually now expanding into like 16 and 18U cubes. What I want to highlight here is something that was touched by Dr. William, and this is that from statistics. Sorry.
Thank you. I think our time is almost up. We should be wrapping up. So just to draw your attention, please.
Okay, well, I almost finished, but the point I was trying to make is that 50% of satellites CubeSat done at university level fail. And the reason for that is because they're treated not in the way that we should treat them as we would do traditional satellites. So traditional satellites look into reliability, understand the effects of radiation, and all these other effects which you need to analyze and do a lot of design work in order to ensure they're successful. Yes, it might be very cheap to design a CubeSat, but the cost of launch is quite high compared to the cost of actually the hardware of the satellite. And I think as time is really short, I will leave it here in case people want to ask questions, but that's it for me. Thank you.
All right, thank you very much. Thank you to you all for your insightful presentations and letting us know what you are doing in your various institutions and countries. I must say the participant, the panel here are very much pleased with what we are all doing as experts in this area. Now, the floor is open for questions and answers. And so to our panel here, I mean the participants in the auditorium and also those online, please, if you do have any question, kindly indicate right now so that panelists or speakers can answer you. I would like to take the lead by asking Dr. Dr. Kissen. Yeah, one question.
Yes,
Dr.
yes,
Kissen.
please.
Yeah, thank you once again for your great work. I just want to ask how you were able to manage a different age group. You mentioned that with your outreach or training program is between age 14 to 21. How were you able to manage the different age group to be able to develop the satellites for launch?
Well, good question. I mean, see, the younger ones think a lot out of the box. So that is the reason we use them for research purposes. And the ages between 18 and 21 are all hands-on. So we kind of get those kids to build the subsystems, to work on the PCB designing, electronics, and the integration. This was integrated by all the 21-year-olds.
Okay, that's good. That's great. And with your sensors, you know, when it comes to Cubesat, most institutions, particularly like Africa, as it being a new area that we are all trying to explore, most African nations are trying to explore, most end up going for commercial off-the-shelf components. That is components that are already built and being sold.
Yes, which has got space heritage and everything. So, you know, what happens if we are going to go off-the-shelf components? It's pretty expensive. Maybe for one satellite, you know, you can, one CubeSat probably you can try, but it is always better to develop everything indigenously. One good thing about India is now it is developing. The chip industry, the electronic industry, and everything is developing in India. PCB boards, if we design, we do have a couple of manufacturers who can actually manufacture and give it. Of course, there are some rare components that we have to procure imported from US or Europe. So we have no other option but to do that. Solar panels, again, still we need to import. So like this, you know, you have small, you know, unique components that go in building the satellite, which needs to be imported. But otherwise, you know, this satellite end to end, we have been able to indigenously build our subsystems and, you know, our PCBs, everything we were able to do it here indigenously.
All right, thank you. Thank you, please. Are there any other questions?
Yes, I want to kind of take it from questions to what we're trying to accomplish. One of the things we're trying to do here with All Nations as the headquarters is a constellation project across different African universities. And so as I'm listening to each person speak, I see the opportunity to really map out a strategic plan to get from where we are now with, yes, we have agreement signed, to actually execute. So we saw that earlier that the programming that Max IQ has can take you in a school year to a basic CubeSat deployment capability, right? So let's say we were to use that piece. Also, Dr. Kissenan's Space Kids program also has some content that can do some of that also in the same school year. I think coming out of this, what we need to do is to have a work meeting, if you will, with each of them individual, and see if we can map out a work program for the universities which have signed on, and identify if there's a team of 5 to 7 students on those campuses that will be leading. They will be taken almost every week. They have to go online. Half of the stuff they have is already online. It's a matter of them meeting as a group, each university, to say every Thursday or every Wednesday night at 7 o'clock, we meet to spend an hour going through the material to go through phase 1, phase 2, phase 3. Some of the kits, for example, let's look at the Cubesat kit that Xavier, that Solomon talked about. He has designed that to be affordable within the African context. So if you say, okay, to build and launch an actual Cubesat will be, we don't have the wherewithal. The government is not going to give us the money. We have to go and raise the money. That's what you figure out. Are you going to sell cookies? Are you going to sell model satellites as jewelry to create excitement? That's part of getting your business school of your universities involved in the process, right? Thinking through who else in the department beside the engineering schools may want to have skin in the game at the university. So you have that happening on the side. So you could be that we can say the first year we will try to raise the money for the actual project, and then just do the online exercises, do the things we can do with simulation modeling by even designing some of our own simulation, and then do the Cubesat project, which is also designed to be very, very low key, because even if you build a Cubesat and complete it, you still have to pay for the launch services if you don't have somebody donating that to you, right? But then it gives you a year. Then you have your second year. Your roadmap could say, okay, by this time we'll have raised the 10,000 or the 20,000 or $50,000 we need. We'll have work to deal with our space agency to give us half. We raise half from the private sector. Now you can complete and have this done. But I think when I hear all the speakers here, I'm really hearing all the pieces are there. It's just for us, to, as Dr. Jadra says, what is the project charter? What are we trying to accomplish as AFCONSAT? And how do we take all these partnerships that we could use here, right here in this room, to move forward? And I'm going to throw the comment and as a question to both Srimati Kesana and Dr. Edmondson and Dr. Omar. From your perspective, given all the content you have, the material, do you think what I just said is a feasible course of action to move from they already have signed an agreement to do it. So that's not the issue. The issue is to actually design the project steps and to do it, which is another question. So based on what you have at your disposal and what we have seen, do you think the rough sketch I've made of the roadmap seems a feasible way forward to get to the goal? What is the goal of your universities to have this done? Was it next year or 20? What is the year when you turn 10? Is it next year you turn 10? But when is Ghana start turning 10? I think you wanted to launch this when you turn 10, right? What year is that?
Yeah. Last year.
You already turned 10.
Yeah.
So when is it going? When was AFCONSAT originally supposed to happen? AFCONSAT 2021, and then COVID hit. So we're now 3 years delayed. So when is your next deadline that you really want to work towards? 2025. Okay. So if we say we're going to launch by September 2025, you have 14 months from today, basically, to get it done. Is that a feasible date? And based on what you've heard today, Ernest and Joseph, is this possible given all the resources you have, low-cost resources, to train the other schools to do what you guys already know how to do it, but you've got to bring the other schools up to scratch. So you're going to be the team lead, but you have content online available from Max IQ, from Dr. Srimati, from Dr. Iman. You have content. It's a matter of you going through and developing the curriculum. And Dr. Edmondson had a proper curriculum that he outlined that could help shape that. So I also want to get some feedback. I see Dr. Iman's hand up. So maybe he wants to take a stab at it first, but I'm seeing the possibility really clearly, and I'm going to give you the mic since you're also part of the team.
Okay.
Thank you.
Thank you, Madam Chair. Dr. Omar can proceed, please.
Yeah, it's very tight to say you're going to launch it next year. Yes, you can build a satellite in 3 months if you want to, but whether it will work or not, that's another story. Your challenges are going to be identifying a launch opportunity, which could take months, but also getting the regulatory requirements in terms of frequency. If you're not using the standard amateur UHF frequencies. But I think most importantly is really what do you want to do with this CubeSat? I mean, if it's just for educational purposes and you know, just launch it on a balloon or just build it and put it on the table. But to launch it, of course, it gives a lot of impetus in terms of encouragement to the students, excitement to motivate them. I think what Dr. William outlined is basically similar to the model we use, which is a three-year staggered approach to be realistic. And I think what you said, Madam Speaker, is the first year really you're spending on trying to work out what you're going to do a lot of simulation analysis. And again, I agree with Dr. Williams. Software might appear to be the simplest, but it's usually the one that causes most problems. And you need to start that as early as possible. So there's a lot of groundwork that need to be done at very low cost that you can start as early as possible while you're thinking about how you get your funding, just as you said, rightly said. But more importantly, really, you need to understand or work out what is it you want to do. You want to do something that's useful, that is going to contribute, and not just for the sake of PR.
Hello. Yeah. This is Dr. Mensah from AATI, also from ENP-HB, Cote d'Ivoire. Congratulations to all the presenters. We really enjoy what you have presented to us. I have a question for Xavier. You said that you are working on the Pocket Cube, and I want to know if your Pocket Cube has an attitude determination control system, and also if we can put the Pocket Cube in constellation. We are very much interested into constellation with Cubesat and the low cost, you know, of Pocket Cube. So can you tell us about that? Thank you.
Okay. All right. Mr. Xavier. Sorry. Solomon. Are you please online? So you can answer Dr. Edo's question. Looks like he's not online.
I can answer that if you want, because we did do these CubeSats. If nobody else wants to answer, I'm happy to answer that.
Okay, then please go ahead.
Just to also make it very clear, it doesn't matter the size of the satellite, whether it's the one I showed in the picture, which is like a bus, double-decker bus, or it's a pocket sat. The amount of effort you need to put into the analysis and the design, and of course, more importantly, the testing. You need to test and test and test in a realistic environment. I didn't show the slide because I went through it very quickly. You need to do vibration testing, you need to do thermal vacuum testing, you need to maybe do, say, AMC testing, all these things you need to do, irrespective of the size. Yeah, what will help you, of course, is the fact that the size is smaller, so you can use a smaller chamber and smaller kit for testing and lower the cost of launch and maybe the cost of materials. But the design effort is not really shrunk, I'm telling you. Software is going to be software, whether it's a huge satellite or small satellite. Even the pocket size satellite, you still need to develop all the software to make sure that you can command it correctly, you can point it to the right way, and of course, in the end of the day, dispose of it for sustainability, space sustainability. So this is something you need to keep in mind in terms of designing. And the other thing, again, I'll say this again and again, because that's the thing that hits us most, is radiation is quite a serious issue. You need to think about things like latch up, which causes the semiconductors to blow up and burn. You need to think of a single event upset that corrupts your software and cause it to crash. And lots of other things. If you've got optics, it might cause it to become opaque. A lot of other things that you need to consider. And again, that's irrespective of size.
Yeah, thank you so much. One of the things we're moving towards in the Cubesat project, if we want to have water domain awareness and security. As we know, with climate change, the issue of water is going to become more and more challenging. And so, because we want to tie the AFCONSAT project into one of the AU agenda items and the long-term processes, whether or not we do it as an experiment to get started, the whole goal is to have capability when a full-blown system is ready to have water domain awareness as a decision support system that can address some of the potential conflicts of the future. We know that water is going to be a conflict of the future. We know that people are buying up swaths of land in Africa. We are not sure why they want this land. So we want to know why they want this land. We don't know what's over there. So we definitely want to make sure that water is not commodified in such a way that we're banning a lot of bottled water all over the world. But groundwater, water resources, the rivers, the way they run, if they're being blocked by some potential, negative warring tribe or whatever, we need to have water security in at every way possible. From the mining pollution of water from ground reserves, that's really one of the major long-term goals of having a constellation run by universities across Africa. So that's the payload goal. So it might be several iterations to get to the final thing, but we do want to get started and get something off the ground, some way of working. Right now we are doing, this is Dr. Nelson, we're doing a project as headquartered at Morgan State. And it's a simple, well, when I wrote the design, myself and Meshach is a team lead actually. When we wrote the concept, we thought it was going to be a very simple concept, quite frankly. I've never seen such a simple experiment take up so much time, right? It's really, why? Because it's complex, because there's 5 universities involved. Number 2, the technology we thought that they said was ready is not ready. So we couldn't get it to buy off the shelf. And at the same time, trying to, work with a university in Australia, a university in Finland, a university in Mauritius, a university in Jamaica, one in the US is a nightmare, just getting meetings organized. And so this is part of the challenge of really doing space. And then when you talk about space for all and inclusion, etc., it's a nice sounding thing on paper, but it's as much harder to do in reality when universities have their own rules, their own regulations. Each country has its own protocol for procurement. Everything becomes, it's not so much the technology sometimes, it's the institutional framework around the thing that makes it so hard for these collaborations to occur. So I really am behind encouraging these universities to persevere and start with the smallest common denominator. If it's to build 6 CanSats and get them up at the same time, even if it's not unofficially a constellation, with something that's similar about them, some data that is going to similar that they can look at, read together, and come up with a paper or something, and then say iterate, and then in the next 2 years they do the next level. But we have got to start moving this capacity building, which is what this conference is about building capacity for long-term sustainability, and my word is regenerative growth, which ties into the whole UN Some of the Future perspective. I think our time is up actually. So I should just go up and close off the meeting officially while I'm at it. And thank Joseph for moderating for us. And
thank you, speakers.
Thank you. I would like to catch up with you later after this meeting, because we're involved in a project called AquaWatch, which I think could be augmenting, or you could be augmenting this project really nicely.
Yes, definitely. We do have to follow up with all the speakers. We're going to be sending out some, I guess, questionnaires of people who may want to persist in continuing this work. This is not a traditional conference, as I said when we began. It's really a gathering to work out some specific projects. So AFCONSAT is one project, and then the Omni Africa Space Exploration Analog Simulation is another project. And because I'm acting as advisor to the ShaktiSat project, we're also here to try and begin to identify some women in the space movement who will serve as focal points and ambassadors to get these girls to the table. So thank you all. Thank you, Solomon.
Dr. Williams,
thank
did you want to say something? Dr. Williams.
Dr. Edmondson, thank you. Dr. Srimathi, thank
Claire,
you.
Dr. Claire,
Dr.
Imam
Omar for being here with us. We appreciate you.
Dr. Imam was saying something, Dr. Claire.
No,
sorry.
I was saying Dr. William, I think he wanted to say something, but.
No,
Yeah,
I was just going to say, it really starts with the science. what is it that you're trying to do? Because the payload really what determines what the other subsystems are going to do. And so it has to be interdisciplinary, multidisciplinary approach. That was all. And I was going to, as part of the feedback, I would definitely promote that.
Awesome. Thank you again. Have a good evening or a good morning or a good afternoon.